Welcome to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. This lecture, Masterclass 9, focuses on molecular symmetry as it applies to polyatomic vibrations. Molecular symmetry can be described as patterned self-similarity. We can discuss symmetry in terms of symmetry operations, which transform molecules to equivalent positions and orientations, or in terms of symmetry elements, which are geometrical entities such as lines, planes, or points with respect to which one or more symmetry operations may be carried out. There are four types of symmetry elements or operations for molecules. The first is rotation about a symmetry axis, and it is denoted C subscript n. It involves rotation by an angle of 2 pi over n about a symmetry axis. We can also define the reflection operation with respect to a mirror plane. This operation is denoted sigma. Rotation about an improper axis is denoted S subscript n. In this case, rotation by an angle of 2 pi over n about a symmetry axis is then followed by reflection in the perpendicular plane. Finally, we can define the inversion operation, which involves inversion of all atomic coordinates with respect to an inversion center. Group theory tells us that successive execution of two symmetry operations must correspond to another symmetry operation for the molecule. We therefore include a fifth do-nothing or identity operation, denoted E, such that we form closed groups. A symmetry group is defined by the symmetry elements that it contains. No two symmetry groups share exactly the same set of elements or operations. For example, molecules that exhibit the symmetry elements E, C2, sigma xz, and sigma yz belong to the symmetry group C2v. Water has C2v symmetry. These groups are named using the notation devised by Arthur Schoenflies. You will become more familiar with symmetry groups if you continue with more advanced study in chemistry, physics, or mathematics. Symmetry groups are often reported in character tables, which summarize the properties of symmetry groups. The rows of a character table are called irreducible representations, which can be thought of as the unique vectors within the symmetry space. The labels that we use to describe these vectors provide a shorthand way of describing the symmetry character of a species under the given symmetry operations. For example, consider the normal modes of water: the symmetric stretch, the symmetric bend, and the asymmetric stretch. We can describe the normal modes of water with displacement vectors. The symmetric motions have the hydrogen atoms moving in phase with one another, while the asymmetric stretch motions of the hydrogen atoms are out of phase. Consider then what happens to these displacement vectors upon execution of an identity operation. Owing to the fact that following the symmetry operation, the apparent motion of the molecule was unchanged, it was as if all the vectors were each multiplied by 1. A C2 operation, or rotation by 180 degrees, leaves the displacement vectors apparently unchanged for the symmetric stretching and bending modes, but reverses the displacement vectors for the asymmetric stretch. Reflection in the xz plane leaves all displacement vectors unchanged, whereas reflection in the yz plane leaves the symmetric modes unchanged but reverses the displacement vectors for the asymmetric mode. If we now examine the character table of these vibrational modes under the C2v symmetry operations, we find that the symmetric stretch and bend have A1 character, and the asymmetric stretch has B1 character. The uses of symmetry go beyond simply providing a labeling scheme for the molecules and molecular vibrations. Vibrational wave functions are also described by symmetry, and we can use the symmetry properties of wave functions to deduce whether or not a vibrational transition is possible. For example, the ground state vibrational wave function is e to the minus 1/2 q squared. Here, q is the vibrational normal mode coordinate, and we see that the symmetry of the wave function is independent of its sign. Thus, the v equals 0 wave function transforms as the totally symmetric irreducible representation of the relevant point group. In contrast, if we use a ladder operator to produce the v equals 1 wave function, we see that psi1 has the same symmetry as the normal mode coordinate. If we continue employing the raising operator on our newly generated wave function, we see that the v equals 2 wave function is proportional to q squared, that the v equals 3 wave function is proportional to q plus q cubed, etc. Thus, wave functions for levels with an even vibrational quantum number must transform as the totally symmetric irrep of the symmetry group, and wave functions for levels with an odd value of V must transform as the symmetry of the corresponding normal mode. Note that this interpretation is only valid for non-degenerate vibrational modes. So if we take water as an example, we can now label each of the vibrational levels with the wave function symmetry. Since our normal mode picture views molecular vibrations as harmonic, we know that for a vibrational transition to occur, there must be a change in the dipole moment during the course of vibration, and the vibrational quantum number must change by plus or minus 1. For polyatomic species, it can be difficult to see whether or not the former is true. Instead, we can consider the transition dipole moment integral. Owing to the fact that the molecular dipole moment is a vector with x, y, and z components, we must consider the x, y, and z components of the transition dipole moment. For a non-zero transition dipole moment to occur, at least one of the component integrands must be transforming as a totally symmetric irreducible representation. Thus, we must determine the direct product of the irreps for the initial vibrational wave function, the dipole moment vector component, and the final vibrational wave function. We already know how to determine the symmetry of vibrational wave functions. To determine the symmetry of the dipole moment vector components, we need only look in the vector column of the associated character table. For example, under the C2V symmetry group, a vector along the z-axis has A1 symmetry, a vector along the x-axis has B1 symmetry, and a vector along the y-axis has B2 symmetry. In determining the direct products for the x, y, and z components of the dipole, we find that the water asymmetric stretch fundamental vibrational transition is dipole allowed along the x-axis. Thus, the transition is IR active with a transition dipole moment that is perpendicular to the principal symmetry axis. It turns out that perpendicular and parallel transitions result in distinct spectra. For example, in linear molecules, only two types of vibrational modes are possible. Sigma modes involve stretching along the bond axis or parallel transitions, and pi modes involve bending motion perpendicular to the bond axis. Here we see an example of a sigma-sigma transition for HCN. The transition exhibits the now familiar P and R branches owing to the delta J equals plus or minus 1 selection rule. For perpendicular transitions to excited bending modes, an additional quantum of vibrational angular momentum is excited. Consequently, delta J equals 0 transitions are possible in addition to the normal delta J of plus or minus 1 lines, and an intense Q branch is observed. Observation of Q branches is also a common occurrence in electronic spectroscopy, where electronic orbital angular momenta often change during the course of excitation. We will explore this further in Masterclass 11. See you next time.